In this presentation, we're going to look at eigenvalues and eigenvectors and something that's related to eigenvectors called eigenspaces. So, what is an eigenvalue? In terms of how to compute it, the eigenvalues are the solution to the characteristic equation. Okay, so for some matrix A, a matrix A would have eigenvalues. Depending on the size of the matrix, so suppose it is a 3 by 3 matrix, it would have 3 eigenvalues. If it was a 4 by 4 matrix, it would have 4 eigenvalues. Essentially what we do here is we compute A, and what we do is construct this other matrix, lambda times I. Lambda is I is the identity matrix, so lambda is a scalar, and we subtract a minus lambda I, subtract one matrix from the other, get the determinant of that, and let it equal to 0. It's best actually probably done in practice. Eigenvectors as solutions to the matrix AX equals lambda x. Okay. Now, what we're solving for here is x, because in this case we would have A and we would have lambda. And what we do there is just solve for x. X would be, for example, x1, x2, x3. It would be a sort of column vector. So you'd have A, which would be, let's say, a 3 by 3 matrix equals lambda times x1, x2, x3. Okay, and what you do is try and solve that. Solve the values x1, x2, x3. There'll be, if there's three, there'll be 3 of these column vectors, and those will be the eigenvectors. Now, the thing about, if you can't come up with a unique solution, you would call it an eigenspace. Okay, we're going to sort of see that shortly, because this example would have eigenspaces. So solutions, the eigenvectors again are solutions for x for this following matrix, this equation here. A times x equals lambda times x for some matrix A. Okay, so let's get cracking. So calculate the eigenvalues and the eigenspaces. Now that's a sort of bit of a hint. You would say we're looking for the eigenvectors, but the eigenspaces is what we're going to get for the following matrix A. Here it is, A down here, 1, 1, 0, 0, 0, 1, 0 minus 2 minus 3. Okay, so first off, let's compute the characteristic equation. Okay, this helps us find the characteristic equation. And A is this part here. Okay, sorry, what I'm going to do first off is just look at the internals here. So just to sort of like compute A minus lambda I. This here is lambda I, the identity matrix times lambda. So that corresponds to lambda I is this matrix down here. A gives us that. And what we do is a case-wise subtraction. So 1 minus lambda gives us 1 minus lambda, and so on. 0 minus lambda gives us minus lambda, and so on. So essentially what we're doing is subtracting lambda from the diagonal. So essentially this is A with a minus. On the diagonals we have minus lambda. Okay. Oops. Now, what we're going to do is solve that matrix. So, sorry, just get rid of this here for a second. This is the determinant. It's the bars at the side. Okay, so now we're going to get the determinant of this matrix here. Okay, so what we're going to do is pick a row or column, and what we're going to do is we're going to pick the first column here. The reason for that is it has loads of zeros on it. Okay, such that what we're going to do is take this cell and multiply it by the its minor matrix. Okay, the minor matrix is everything when you don't include the row for this cell. So essentially all the values that are not on this row or column. Essentially these ones down here. So what we're going to do is get the determinant of this submatrix here. This 2 by 2 submatrix. Okay. And it's the matrix you get when you omit the row that this is on, I minus lambda, and the column it is on. So we're just left with that matrix down there. That is here we go. You continue on, but because we were picking a column with loads of zeros, the rest of it is trivial, so we can just ignore it. So we only need one part of it. The first elements, because we're going to multiply this by the determinant of that, then multiply that by the determinant of its minor matrix, and that by the determinant of its minor matrix. They're both zero, so it's a trivial. It doesn't give it yields anything. So when we have the first one done, we can stop essentially because all the other terms are going to be multiplied by zero. Okay, so that's why we can stop there. I won't get too much into how to calculate the determinants of 3 by 3 matrices because that's not really what this is about. You need to know it, but it's not really important here. So this is the matrix we're going to get the determinant of. Okay, so A times D minus B times C. So A minus lambda, D minus 3 minus lambda, minus, okay, minus 2 B and, or sorry, C, and lambda, or sorry, C, B is that. So it's just a straightforward multiplication for it's a straightforward determinant. What we're going to do is multiply that determinant, that's it there, by 1 minus lambda. Okay, so this is building up our characteristic equation here. That is our characteristic equation. Actually, what we're going to do is solve this. I'm going to just simplify this. This is 1 minus lambda. The minus signs can cancel out. So we have 3 lambda plus lambda squared plus 2. Okay, minus times minus 2 times 1 just gives us plus 2. This part here, I'm just going into the next slide here, that is 1 minus lambda. That part here, this part here can be factorized. We're interested in factorizing it. If we multiply it out, that gives us the full form of the characteristic equation. Well, we're interested actually in factorizing it. So this is lambda plus 2 times lambda plus 1. Now, that's the characteristic equation done. And what we do is let that equal to 0. So this is the important part. So we have that the characteristic equation factorized, and we let it equal to 0. So now we are able to determine the 3 eigenvalues. Okay, sorry, where am I gone there? So there they are. Lambda, 1 minus lambda, that will give us 1. Lambda plus 1, that will give us minus 1. And lambda plus 2, that will give us minus 2. I'm actually going to sort of very deliberately put them in ascending order from the bottom. So minus 2, minus 1, and 1. The reason for that is because the ordering does matter for calculations that happen later on. So I'm going to keep so the ordering is very, very important. Just as a sort of minor remark, this is actually relates to diagonalization later on. That this is actually related to a subsequent presentation. We have 3 different eigenvalues. So what we could say is A is diagonalizable over the reals. Now that's sort of, I'm not going to really get into that in this presentation, but I'm going to come back to that in future presentations. Do you know what? I'm going to stop there and I'll pick up on eigenspaces and eigenvectors now in the next presentation. Eigenspaces. Where am I gone? Okay, stop.